The title of my main project is Prediction and Detection of Seizures based on Wilson-Cowan modeling. This basically pertains to epileptic seizures. Epilepsy is a common chronic neurological disorder affecting 60 million people worldwide. Epileptic seizures result from a sudden disturbance of brain function which is characterized by abnormal discharges of cortical neurons recruiting neighboring cells into a critical mass. Firstly, when we look into the Wilson-Cowan modeling, the Wilson-Cowan model is represented by the diagram that has been shown on screen. This is basically a mechanistic model. Mechanistic refers to the fact that the model is based on neurophysiological insight into brain processes. A qualitative model of seizures is that the brain assumes that the brain has two potential dynamical states, a normal and a seizure state. Random fluctuations in the brain can induce the seizure state in epileptic patients. The Wilson-Cowan model consists of two coupled differential equations, as is shown, wherein Py and In represent the excitatory pyramidal population of neurons and In represents the inhibitory population of cortical GABAergic interneurons. Various other constants such as tau I represent timescale constants, hi represents the inputs, ci connection strengths, and theta represents the slope of the sigmoid function. A sigmoid function represents the non-linearity and is crucial for the self-organized behavior of the model. Going back to the figure that represents the Wilson-Cowan model, it is assumed over here that the pyramidal population represented by the variable Py excites the interneuron population. This excitation is represented by the constant C2 as a positive C2, and the pyramidal and the inhibitory population inhibits the pyramidal neurons by C3, and this is represented with a negative sign. Moreover, the self-excitation property of pyramidal neurons is seen by the constant C1 and the positive sign. These are being included in the two equations with appropriate positive or negative signs. Now, when we look into the MATLAB code that has been written and executed, the file name being model_final.m, here I'm basically trying to initialize the array dx dt. I'm trying to initialize the array dx dt and then set up a prompt wherein I ask the user to enter the estimated population by taking into account various constant values and representing the equations that we just saw in MATLAB format. When I try to run this program, I have it displays I'm asked to enter the population of pyramidal and cortical neurons respectively. Let's assume I'm entering 1000 and 10,000. Then my output is 49.1016 and 990.95. This goes to say that when an epileptic patient is suffering from a seizure, and if the populations of pyramidal and inhibitory neurons is assumed to be around 1000 and 10,000, then at any instant of time 49.10 pyramidal and 990.95 inhibitory neurons are responsible for the seizure. Having dealt with EEG modeling, now we move on to the second phase, that is prediction of seizures. In prediction of seizures, the dynamics of EEG signals are analyzed by presence of positive zero crossings. Positive zero crossings means the signal value changes from negative to positive. In this algorithm, a Gaussian kernel is employed. The window width depends on the standard deviation represented by sigma and is calculated by the following relationship. Having calculated the window width we can compute the probability density distribution function and the differential entropy, and depending on the presence of zero crossings of the differential entropy, we can decide or categorize the EEG data to be that either coming from a normal patient or an epileptic patient. When this is executed into a MATLAB code, in this program, initially we're trying to read EEG data. Then by using Nyquist theorem, we try to we design an IIR notch filter, and we try to eliminate the 50 Hz interference, that is the noise signal. Later on, the signal is sent through a low pass Butterworth filter, and we only extract those frequency components which are required for us, which is basically the low frequencies, because high frequency only contains noise, which is highly undesirable for any processing methodology. And because the probability density function and depends on the window width, which in turn depends on the standard deviation, we calculate the standard deviation as subtracting each point from the mean value, and having obtained that, we write a for loop and try to calculate the probability density function as well as the differential entropy. After calculating the differential entropy, which is log of the PDF, we plot it, and depending on the plot, that is, if at all in the entropy, if there is if a zero crossing is present, then we can say that it belongs to an epileptic patient, or the patient may suffer from an epileptic seizure within few seconds to milliseconds. And if there is any absence of epileptic seizures, absence of zero crossings, then it is a normal data and the person will not be suffering from epileptic seizures. When I run this program, the first is my input signal, that is this top signal is one that is unconditioned, that is along with the noise, and the second EEG signal is that which is being pre-processed, that is devoid of high frequencies as well as 50 Hz noise. Then my output, which is a plot of the entropy, is seen as a graph that has a slightly negative value, and then at when the x coordinate is at 4, it shoots high, very high, following showing that the entropy has experienced a zero crossing. This sudden rise in entropy goes to say that a seizure is likely to occur in the coming time. The third phase of the project is that of detecting seizures while they occur. In detecting seizures, firstly we input EEG data and we pre-process it, that is by designing an IIR notch filter with a stop band at 50 Hz, such that the 50 Hz is eliminated, and we use a Butterworth low pass filter in order to pass only low frequencies and to obstruct high frequencies. Then by using wavelet analysis, that is by using dB5, that is Debauche's wavelet of order 5, we extract the detail coefficients, reconstruct them, and then display them in a single window using the subplot function. Now, having extracted all the detail coefficients, wavelet coefficients, we try to compute the maximum, minimum, mean, as well as the standard deviation of these coefficients. These values are then given as inputs into a new fuzzy inference system. As can be seen, ds is equal to new FIS. In this statement, ds is a variable that is that stands for detect seizures, is equal to new FIS, that is the new fuzzy inference system, and I give the name of my fuzzy inference system. Then I'm trying to add a variable for the maximum wavelet coefficient, which will be which would obey the membership function given by the sigmoidal membership function SMF, whose range is from 200 to 200 because I wanted a vertical line. And accordingly, I'm also trying to, similarly, I'm trying to add further variables as well as respective membership functions for the minimum, mean, as well as standard deviation of wavelet coefficients. Then the output would be depending on the 4 input values. my output is designed such that it can either belong to an ictal dataset or a normal dataset, that is either a seizure dataset or a normal dataset. Later on in my rule list, I'm specifying the weights as well as the relationships of different in between different inputs to the output. Now when I try to run this program with S15, that is an epileptic data set, my output is as shown. Trying to analyze each output. Firstly, the first half of it consists of an unconditioned EEG signal, and after performing pre-processing techniques, I get a conditioned EEG signal. Then these are the wavelet coefficients that we have reconstructed using a Debauche's wavelet of order 5. These show the membership functions that I chose for designing in the fuzzy inference system. The first one for maximum wavelet coefficient is that whenever it exceeds 200, that is whenever the input exceeds 200, in that case we can say that it belongs to, the data is from an epileptic patient. Or when the minimum is lesser than minus 200, when the mean is greater than 30, and when the standard deviation is greater than 50, then we can say that they all belong to an epileptic patient, and a seizure is occurring as we speak. Now this is the rule viewer of for the fuzzy inference system. Here we can see that the input is given as 500, minus 400, 50 and 75. 500 being that of the maximum wavelet coefficient, because we've designed the system such that if at all it exceeds 200, it is indicating an epileptic seizure. 500 is much greater, so it is in the shaded region. Similarly for minimum, because we specified it to be that from an epileptic seizure when it is below minus 200, so minus 400 is well within the range. 50, again we have specified greater than 30, and for standard deviation we have specified it to be greater than greater than 50, so 75 is a much higher value. And keeping all these in view, the fuzzy inference system has given an output value of 0.2, which can be seen over here. This is the output membership functions, that is from 0 to 0.4. If at all the detect is equal to 0.2, if at all that value is anywhere from 0 to 0.4, it is representative, it's representing that an ictal set, and if at all it's from 0.5 to 1, it is representing a normal set. Because we have got detect is equal to 0.2, and because 0 to 0.4 belongs to ictal, we can say that a seizure is occurring at the moment, and this is how we detect a seizure.